Hi everyone, I'm Carolin, and this is From Text and Graphs to Explainable Knowledge. Today, we live in a world where every day we generate more and more data. And even for a specific topic, for example, biology, we generate more data than a single human could read. So a key question is, how can we leverage this wealth of information? At NEC Labs Europe, we organize data in knowledge graphs. And then, based on a knowledge graph, we infer new knowledge using AI technologies. Here's a small example of a knowledge graph where we have different nodes that are connected by relations. As an example, we have Space Needle is located in Seattle. And we will see how, based on such a knowledge graph, we can train an AI system to predict new knowledge. Here is one more example of a knowledge graph. This one explains a bit the background of the lab that I work in. So NEC Labs Europe is a research lab, which is part of the NEC Corporation. NEC is a Japan-based international company, and in total it employs about 110,000 people. We interact with NEC as our lab by researching and then transferring the output of our research. And in turn, we also look at the business application of our company and what problems there are. And this inspires our research on how we can improve those products. In our lab, there are about 85 researchers, and we're located in Heidelberg, Germany. We have quite a few very different groups researching different topics. I myself am a member of the machine learning group. And there I, of course, collaborate with the other members of my group, but I also closely work with the biomedical AI and the AI innovation group. And in particular, there are two collaborators I want to highlight here, Timo Stiller and Matthias Niepert. Timo and Matthias were my co-authors in the main work that I'll be presenting today. Some more details about the machine learning group. It has two main research themes. The first one is graph AI. Under this topic, we explore how to best learn graph representations. And also, given a knowledge graph, how can we use AI to infer new knowledge? And what do we even do when there is no graph yet? And for this, we've developed a framework where we can extract a knowledge graph directly from text. And also, we apply this to multilingual text. The second research theme is newer. We call it modular, adaptive, and explainable AI. Here we want to explore such topics as more human-centric AI, or how can we quantify the uncertainty of a prediction, or how can we combine deep learning and reasoning. In the talk today, we will see how we can go from using information extraction to turn text into a graph. And then based on this graph, we can use graph AI to infer new knowledge. And here we've seen that we really need to explain to a human user why new knowledge was predicted. And for this, we've recently developed our method called gradient rollback, so that now when we predict new knowledge, we can also explain why this was predicted. In the talk, we'll look at one concrete application example, which also in part motivated this work, and that is predicting polypharmacy side effects. So let's have a look at what that means. Polypharmacy means that someone is using more than one medical drug at the same time. And often when someone does this, there can be unintended side effects. So it's of course important to know whether such side effects can occur before two drugs are taken by someone. However, there are a couple of problems. And the first one is there are, of course, many possible combinations of drugs that someone can take. So which two drugs should a researcher investigate if they have a side effect or not? And choosing such a combination is often more trial and error. At the same time, once the researcher picked a combination, they will run experiments in a lab with the actual chemicals, and this will be very time and resource consuming. So the question is, how can AI help in this process? And we can do this in the following way. The whole idea of someone taking a medical drug is that a drug will target a protein in our human body, and this in turn will cure the disease or illness. So what we can do is we can take all the knowledge that we know about already from previous research, and we can model this knowledge in a knowledge graph by depicting drugs, proteins, and the relations between them. And then based on this knowledge graph, we would like to train an AI system that can then predict what the likely side effect between two previously unseen drugs is. So as a brief example, here's a toy picture of such a knowledge graph, where we have drugs, which is the symbols with the cross in the middle, and we also have proteins. And then we have relations between drugs and proteins, and also between two proteins. And this information is based on previous research. Now, in this example, we don't know anything about the top two drugs in this knowledge graph. The left one is polypharmacy and the right one is calcium. And our question is, what would happen if those two drugs were taken by someone in conjunction? And this is exactly the kind of side effect that we'd like to predict with our AI model. So to map the talk onto this problem, we have 3 steps. In the first step, we take all the relevant information, and we want to extract the information from this text. And we then, from this extraction, we then build the biomedical knowledge graph. Next, in the second step, we then take this knowledge graph to predict novel drug-drug interactions. And here we've noticed also in other applications that for humans it's very important to know why a certain prediction was made. So our third step is to explain the prediction. And this is the main part of the talk today. Let's, however, first look at the first step, where we extract knowledge from text to build our knowledge graph. The workflow is as follows. We collect all documents of interest, and then for each sentence in the documents, we will extract triples. And a triple consists of a subject S, a relation R, and an object O. And whenever these triples overlap in subject or object, we can use this to then arrange these triples in a knowledge graph. Concretely, we do the following for one example sentence. And this is based on an internally developed framework, which we call neural sequence prediction. And in the background, what it basically does is it takes a sentence and then applies a BERT transformer style model to it. And for each token in the sentence, it will classify whether it's part of a subject, a relation, or the object of a triple, or none of them. So in our example, we have the following sentence. We find that calcium upregulates the protein MMP2, and MMP2 connects with LPAR1. Now, for each word in that sentence, we make a decision whether it belongs to the triple or not, and which part it is. So calcium here is the subject of the first triple. And upregulates is our relation. MMP2 is the object. And MMP2 is also the subject of the second triple, where we also have the relation connects and the object LPAR1. And as you can see, these two triple overlaps via MMP2. So at this point, we can then connect these two triples to form the beginning of our knowledge graph. So ultimately, with this step, we can go from unstructured text and transform it into a knowledge graph, which consists of triples. Now, given our knowledge graph, we can proceed to the second step, which is building an AI model that can predict the polypharmacy side effects. So based on the current knowledge graph, with all the knowledge that we've assembled in it, we would like to now infer what happens if I take polypharmacy and calcium. And for this, we can build a model which is also known as knowledge-based completion, which does exactly what we needed to do. It can predict new relations between entities. So such an AI model might say, taking polypharmacy and calcium together will likely cause pain. Now, if we give this prediction to a human user, they will naturally ask, why does the model think that? Why does it make this prediction? Why is pain the likeliest outcome of taking those two drugs? So can the model explain such a prediction? And to answer this question, it largely depends on what model was used to make the prediction in the first place. Let's look at 2 examples of them. In our lab, we've developed a technology called KBLearn, and it basically is a combination of experts. And here we'll look at 2 of them. The first one is called the relational expert. It takes rules and then applies them to see whether or not a rule holds for the current prediction that we want to make. So as an example, we have A located in B and B capital of C. And from this, the rule derives that A is also located in C. So later on, when we have exactly this pattern again, we can automatically derive that A is located in C. And because of the very nature of how these rules look and work, they're immediately explainable. And when you show them to a human user, they will understand them. And for this reason, the relational expert is preferred in practical applications. However, there is a better model out there, and that's based on a neural network. This one is called the latent expert. The latent expert takes the graph structure, which consists of nodes and edges, and then it turns these into latent representations and can then predict new edges. This model is better, but it's not directly explainable. So the question is, how can we make the latent expert explainable? Now, before we start thinking about this, there are 2 important concepts to keep in mind when thinking about explainable AI. And the first term is a black box. So what we mean by a black box is an AI system whose predictions cannot be explained or cannot be understood by a human user. And we just saw in the previous slide that the latent expert is one such model. And this is in fact typical for neural networks because they just consist of large weight matrices, and a human can't follow why they predict what they predict. At the same time, though, neural networks typically perform best these days on many tasks. So the key question is, how can we make neural networks explainable? But we don't just want any explanation, we want an explanation that is faithful. And this means that the explanation represents the true reasoning process of the model. To illustrate what I mean by that, I want to give a counterexample. If someone asks, why is the sky blue? One potential explanation could be because someone painted it blue. Now, while this is an explanation, it is not faithful because it's simply not true. So when we have explanations that explain our prediction, we want this explanation to be faithful, which means that it presents the true reasoning process of the model. And this is exactly what we kept in mind when we developed gradient rollback, which we want to then use to explain why a new knowledge was inferred by our AI model. The goal is that we have faithful explanations, and gradient rollback does this by explaining a particular prediction, and there it checks which training instance had the largest impact on making a prediction likely. We apply gradient rollback to a model family called neural matrix factorization. And the latent expert that we want to explain because of our polypharmacy side effect application is has such a model underlying it. So neural matrix factorization models can be applied to such knowledge-based completion problems, and they can also be applied to recommender systems, which we'll also look at later. What is novel about gradient rollback is that we can provide a theoretical bound on its approximation error. And we also evaluate the faithfulness of the explanations that gradient rollback returns empirically. Now let's head more into what gradient rollback actually does. And this part consists of 4 parts. The first is the application. What exactly is a neural matrix factorization model? And then we will look more closely at the method itself, gradient rollback. After that, very briefly, we look at the proof outline, which can be used to derive the theoretical guarantee. And finally, we'll look at empirical results, where we evaluate the faithfulness of the explanations that gradient rollback returns. And with that, let's head into the first part, which is what is a neural matrix factorization model. Let's briefly recap. We've seen this knowledge graph already, but let's just briefly look at some terminology. So we have here the triples, which are subject, relation, object. So Space Needle would be a subject located in the relation, and Seattle the object of this triple. Then all the nodes in the knowledge graph are the subjects and the objects, which we also call the entities E. And between two nodes is an edge, which is the relation R. Now, when we train a neural matrix factorization model, then we assume we're given a training set, and that is simply the set of known triples. What exactly does a neural matrix factorization model now do? It maps each entity and relation that we have in the knowledge graph to a vector representation. And then based on this vector representation, we can compute a scoring function f that judges how likely the triple is. There are many possible choices for the scoring function. Here we focus on one that is called dismal, because it's simple yet very competitive, and it works by calculating the inner product of the three vector representations of our triple. The learning process for such a model is finding good representations. And this can be done via gradient descent, where we increase the likelihood of the known triples. Let's finish off our example by looking at what a gradient rollback explanation would look like in this case. First, we record the influence during training. This means that when we see a training instance, we track how the parameters of the model change based on this training instance. So during training, we, for example, see the triple Seattle located in USA. And based on this triple, we will make an update to the neural network's weights, and we record this change in parameters. After training is done, we can use exactly this influence to explain a prediction. So the model will now make some kind of prediction. In our example, this is that Volunteer Park is located in USA. And we want to explain this prediction by saying which training instances increase the likelihood of this prediction the most. And here, for example, we have that Volunteer Park has a sculpture of William H. Seward, and also that William H. Seward is born in the USA. So based on these facts, those were the reason why the model increased the likelihood that the Volunteer Park is also located in the USA. Let's now look into detail on how gradient rollback works. Gradient rollback consists of two steps. In the first step, we're tracking gradients. This happens during training. So as we update the model's parameters during training, we record the influence each training instance has on the model's parameters. And below you see how this works in detail. So our goal is to track the influence of a trained triple D prime. So for the current training triple, we can see what its previous influence was when it was, for example, seen previously during the training step. And then we also compute the gradient from applying the loss for the training triple D prime at the current time step. And together with these values, we can then update the influence for the trained triple so that we know its contribution to the parameter values at time step t+1. Once training is complete, we get to the second step, where we roll back the influence to explain a prediction. This means that for each prediction, we want to identify which training instance had the largest impact on making the prediction likely. Let's now look how this works in detail. So assume we want to explain a prediction D, then we do the following. We iterate over each training instance D prime. And the first thing we do is we remove its influence that we recorded in the first step. That means we take the final model weights and subtract from that the influence of D prime on the parameters of D. Concretely, this means that our training instance D prime can actually only influence the prediction D if they have at least one triple part in common. Now, with this update, we save these newly modified weights under the name WGR. And now we will use these weights in the next step. So in the next step, we have the modified weights, and we again run our prediction D and check how likely it is under the modified weights. Now, if this probability is smaller than under the original model weights, then we know that by removing the training instance D prime, we cause the prediction probability to drop. And therefore, this makes it a possible explanation candidate. So once we've done this for every training instance in our training set, we can split the training set into two parts. Either a training instance caused the probability to drop or it did not. And all training instances that caused the probability drop will be in our list of explanations. In a further step, we will then rank this list so that the top one explanation will be the training instance with the largest probability drop if it were removed from the training set. So this is how gradient rollback derives the explanations. Let's now look briefly at what the outline for the proof for the theoretical guarantee looks like. Crucially, the usability of gradient rollback depends on whether or not its approximation error is small. Or in other words, how well can gradient rollback approximate the influence of a training example? And for this, we compare two quantities. The first quantity is the approximation of gradient rollback. And here we again use the weight modification that we already saw in the previous slides. So we have the model weights that we got when training on all triples, and from that we subtract the influence of the current trained triple D prime that we're looking at. These modified weights we give to the scoring or loss function to compute the value for our prediction D. This is the first value. The second value comes from the true behavior after retraining. So in this setup, we take the training set but remove the training triple D prime. And then we retrain the model and get a new set of weights called W prime. And this set of weights is again given to the scoring or loss function to check the value for the prediction D. So overall, now we can compare the approximation of gradient and of gradient rollback as well as the true behavior after retraining. And if the difference between these two quantities is small enough, then the approximation error of gradient rollback is small. For the full details, I can refer to the paper, but ultimately what this allows us to establish is that gradient rollback can approximate for any training instance D prime in the training set the changes of a scoring or loss function one would observe if a model were to be retrained on the training set but without the training instance D prime. And this also allows us to establish that the approximation error is an expectation lower than known bounds on stability of stochastic gradient descent. Let's head into the next section, which are the empirical results, where we generate explanations using gradient rollback and then evaluate how faithful they are. So just to briefly recap, faithfulness means that the explanation that we're giving truly represents the reasoning process of the model. And we evaluate this in the following manner. For each prediction, we use gradient rollback to identify the explanations. We then remove those explanations from the training set and retrain the model from scratch. And we can then check how the prediction changes with those explanations missing. Based on this, we can define two metrics. The first one is PD percentage. Here we measure the percentage of times the prediction probability drops if the explanation is removed from the training set. The second one is TC percentage. Here we measure the percentage of times the top one prediction changes. This is important for our experiments because we exactly want to explain the top one predictions of a model. We apply our method to 3 data sets. 2 are from knowledge-based completion and 1 is a recommender system dataset. The first one is nations, and this one is rather small. And then we have the 2 bigger datasets, FB15K237 and Movie Lens. We compare gradient rollback to a baseline called NH, and NH randomly deletes neighboring triples of the prediction. We give here a few results. For more combinations, please see the paper. And concretely here, we look at 2 data sets and the PD percentage metric. We also vary the number of explanations that we delete. So we have a setup where we delete just the most likely explanations from gradient rollback, or the top 10 likeliest, or all explanations identified by gradient rollback. And always in comparison, NH deletes the same number of random neighboring triples. As we can see, in all 6 setups, gradient rollback outperforms the baseline. In another experiment, we compare gradient rollback to triage. Triage is the previous best method for this kind of problem, but triage is very slow. For this reason, we could only run the experiments on the smaller nations dataset. Here we report the TC percentage, and we again vary the number of deleted explanations, where we have now 1, 3, 5, and 10. And again, we can see that gradient rollback outperforms the baseline, and also that gradient rollback is much faster than triage. There is one more experiment that we wanted to run, because we know that theory, when we derived our approximation error, we saw that smaller Lipschitz constant leads to a more stable algorithm, which means that that makes gradient rollback better because the approximation error will be smaller. And we wanted to validate this empirically in practice. So we set up the following experiment. In our original experiments, we used no regularization. So now in this experiment, we use regularization, which lowers the Lipschitz constant, and we can measure its empirical value during training. After training, we can again use gradient rollback, and we identify the most influential explanation. And with gradient rollback, we estimate how the prediction probability would change without this explanation. Then in the next step, we remove this explanation from the training set and retrain. This allows us to record the true retrain probability that we get when this explanation is truly not part of the training set. So now we can compare these 2 values. On one hand, we have the estimated prediction probability. On the other hand, we have the true retrain probability. And then we can measure the Pearson correlation between these 2. And here are the results. In total, we have 4 models. The leftmost model is the original nations model that has no regularization. And as we can see, the empirical Lipschitz value L is the highest out of all 4. At the same time, the Pearson correlation R is the lowest, although with 0.81 it's still quite high. In the next model, we apply a maximum norm on the model's weights with a value of 3. Here we can see that the empirical Lipschitz value slightly drops, while Pearson correlation slightly rises. If we change the max norm to 2, we see a quite large drop in the empirical Lipschitz value, and again a rise in the Pearson correlation. And finally, we have the last model with the strongest regularization, which is applying the unit norm. And we can see that this leads to the lowest empirical Lipschitz value and a near-perfect Pearson correlation of 0.97. So with this empirical experiment, we could confirm what theory already told us, which is that if we have a lower Lipschitz value, we have a more stable algorithm, which leads to a higher Pearson correlation, and that in turn means we will have more faithful gradient rollback explanations. So let's summarize what gradient rollback does. The goal of gradient rollback is to faithfully explain a neural network's prediction. And it does that in 2 steps. In the first step, gradient rollback tracks the gradients. This means that during training, we record the influence each training instance has on the model's parameters. In the second step, once training is over, we can roll back the influence. And this allows us to explain a particular prediction by finding out which training instances had the largest impact on making a prediction likely. We apply gradient rollback to neural matrix factorization models, and for those kind of models, we can derive a theoretical bound on gradient rollback's approximation error. We also confirmed empirically that the explanations that gradient rollback returns are more faithful than baseline methods. And now that we've completed this as a research project, our next step will be to actually apply gradient rollback for our application of the polypharmacy side effect prediction. So let me summarize overall what I've talked about today. I introduced the machine learning group at NEC Labs Europe, where we have two research themes. The first one was graph AI, and the second one is modular, adaptive, and explainable AI. In graph AI, we have two technologies. The first one allows us to extract knowledge graphs from text, and the second one, KB-learn, allows us, given a knowledge graph, to infer new knowledge. This has different applications, and the one that we looked at today is the polypharmacy side effect prediction. And because such a polypharmacy side effect prediction, when we give this to a human user and say, taking these two drugs together will likely cause pain, a natural question they have is why. So we were motivated by this to find a way that we can explain our latent expert in KB-learn, which had the better performance for polypharmacy side effect prediction. So now under our research theme for explainable AI, we now also have the gradient rollback technology, which can explain the latent expert in KB-learn. And with this, we can also do one more final prediction on our knowledge graph and say gradient rollback will in future be applied to the polypharmacy side effect prediction problem. And our explanation for this would be because gradient rollback gave us promising research results, and polypharmacy side effect inspired the development of gradient rollback. And with this, I'd like to thank you for listening, and I'd be happy to answer questions.